Hello and welcome back to the lectures on high performance scientific computing. Today we will start discussing a little bit about shared memory programming, more specifically with respect to OpenMP. All the slides that are presented today were originally presented at the Argonne Training Program on Exascale Computing 2024 at the Argonne National Labs. We thank Argonne National Labs for sharing this content. So, we will discuss the introduction to OpenMP. We will talk a little bit about creating threads, synchronization, how to create parallel loops, how to interact with the data environment, what is the memory model that is being used in OpenMP, how to deal with irregular parallelism and tasks. We will look at a recap of all these concepts, and then beyond the common topics, we will look at work sharing, synchronization, and also on how to use OpenMP to program your GPU. We will also look at concepts like thread affinity, data locality, and what is thread private data. So, to give you a brief nutshell about what OpenMP is, it's essentially an API or an application programming interface for writing parallel applications. Typically, the workflow of any research group is such that they usually have legacy serial codes which they have been using for their scientific tasks. Now, due to needs, you would like to execute these codes in a much faster manner, or you want to work with larger sets of data. It is not always convenient to go back to the drawing board and restart writing all the programs from scratch. So OpenMP sort of provides a convenient segue into exploiting parallelism on the hardware by using a set of compiler directives and library routines. It really simplifies using existing Fortran, C and C++ programs and making them multi-threaded and parallel. Newer versions of OpenMP also help us to deal with non-uniform memories, help us to deal with vectorization in hardware, and also GPU programming. So the scope of OpenMP has really expanded over the last couple of decades. So the complexity of OpenMP, the original start of OpenMP was somewhere around the year 1997, and you started writing the specifications for OpenMP, as in like what would OpenMP deal with. And the number of specifications in terms of the actual pages of the specifications that were written has grown a lot, as you can see from this graph, from OpenMP version 1 onwards. Initially, the specifications were mainly with Fortran and C, C++, which were written separately. Then both these specifications were sort of merged. And as we come into this decade, we have newer and newer specifications which include how to deal with GPUs. Obviously, all the features that OpenMP offers today is quite overwhelming, and it's going to be very difficult to cover in a short course. But what we will try to cover is the most common items that are being used by OpenMP programmers. If you look at the common core, most OpenMP programs will use typically these sort of 21 items or 21 pragmas, functions or clauses. They typically decide which sections of the program are parallel. They deal with things like how do I set the number of threads, how do I get my identity or what is my thread identification number, how much time it is taking, because timing is pretty essential. What are the synchronization points, which data members are critical, and how to deal with loops, so on and so forth. It also gives us a few advanced techniques of scheduling, which we will cover a little later. Now, going ahead, let's talk about some basic definitions and what does the basic solution stack look like. At the bottommost, you obviously have the hardware which has all the parallelism which is there to be offered at the microprocessor level. Now, this could be in terms of multiple CPU cores, as is shown over here, which have some sort of shared address space or common memory where all these CPU cores have access to. Each of these CPU cores might have some SMD or vectorization units as well, or you could have GPU cores, which is somewhat separate. So, this is the underlying hardware on which the OpenMP code will actually run. Now, on top of this, you need to have the operating system, which shows support for the shared memory and for multi-threading. You need to have the OpenMP runtime library, which will actually give information to the operating system for scheduling the OpenMP threads onto this hardware. Then at the programming interface, you need to have the directives. You need to have a compiler which now detects these directives, parses it correctly, and then calls the appropriate OpenMP library functions to create threads, to assign work to threads, so on and so forth. It also needs to initialize certain environment variables which is required by the OpenMP library and also by the directives to have a proper syntax for programming. And finally, at the top, you have your application and your end user who is actually programming using these directives. So your algorithms now need to sort of be aware that we are using the shared memory programming, and you need to be sure about what are the different nuances involved in using a shared memory machine. So you can see the level of complexity that is there. For the next few slides and few lectures, we will just be talking about a symmetric multiprocessor case, which is basically a multi-core CPU, which has a shared address space. We are not going to deal with non-uniform memory access, nor are we going to deal with GPU cores at this point of time. We are going to assume that all the multiple CPU cores which are available to us are effectively the same. They all can address the same shared memory space, and that's how programming is going to proceed. We will introduce the complexities of GPUs, etc., at a later lecture. So, one of the things that we need to understand here is that we can now run lots and lots of threads on these multiple cores. Typically, we are limited only by the number of multiple cores that we have on our machine, and a lot of these threads will roughly have the same cost for accessing memory. As I said earlier, we will not deal with NUMA type machines in this lecture. So, what is the most simple syntax for OpenMP? So, these are the C, C++ and the Fortran equivalents. Typically, bits of code have compiler directives which begin with symbols which look similar to comments, which says hash pragma OMP construct and with whatever clauses. With Fortran, you'll have exclamation mark $OMP and then whatever construct. For example, you'll have a hash pragma OMP parallel private X. So parallel is a construct which says that the program section which is coming below between these curly braces is essentially to be run in parallel, and it has some other clauses, something like which says that the variable X is private. We will talk about what private variables are later. We also need to use function prototypes and types. For that we need header files, and for that we have a hash include OMP H over here, or you need to use the OMP library in Fortran. So the way it works is that OpenMP constructs typically applies only to a structured block of code which follows immediately after the directive. So for example, on the C, C++ side, you can see that you have an OpenMP directive over here, and the structured block of code is between these curly brackets. Whereas in Fortran, you have to explicitly start with the structured block of code and end with the structured block of code and not use these curly brackets. It is also fine to exit the program within a structured block. It's okay, and it will kill the program. So here is a very simple program which prints out hello world. Now this is the serial version of the code, which most of you already understand how it works. So you have hash include stdioh, which basically looks at standard input output, and you're saying printf hello world. Now, if I want to parallelize this program, what I really need to do is essentially include this pragma, which says hash OMP parallel, and then it says whatever is below this now is a multi-threaded program and multiple threads will be started. And then you also have to give the compiler the information that this needs to be compiled as a multi-threaded program using the OpenMP environment, and for that you need to give a flag minus f OpenMP. It all depends on the kind of compiler that you're using. The flag will be dependent on the compiler that you use. For GCC, it is minus f OpenMP. For certain other compilers, Intel compilers, it could be Q OpenMP, it could be f OpenMP for ICC, so on and so forth, depending on the machines that you're using. More importantly, you have to see that you have this hash OMP pragma. So what is essentially happening over here? So you will see that you have an OMP include file, which basically tells that, okay, if I want to get to some OpenMP library functions, I can call them using this header file, or the references to those functions are there in this header file. Then it essentially says that this is the parallel region over here where it begins, and it starts with a default number of threads. Now, the default number of threads could be anything, right? It is system dependent. You can explicitly set it at some point if you want. We will show you how to do that too. But right now, we will just take some default number. So now I am going to give you an example run this particular example on my machine and show you how the output works. So for that, I will now switch to my terminal. And here I have a program hello world.c. Okay. You'll notice that my hello world is slightly different compared to the hello world that was in the slides, but we will make it equivalent. So I will make this the same program. Okay. So now we have a very similar hello world program. You can verify the program in this way. Now, the next step will be to compile this program. To compile this program, I invoke my compiler. In this case, on this machine, it is GCC version 14, and I compile it with the flag f OpenMP. I give it the source file, and I say I want the output to go to an executable named hello world. And now you'll see that I have an executable named hello world. So I will execute it now, and you will see a certain output come out. And you can see that there are different hello worlds which are coming out. You can see that roughly about the program outputs about 8 hellos and 8 worlds. If I run it again, you see the output of it is slightly different. It is not the same consistent hello world. Now we will try to analyze why this happens. Going back to the program, what you see is that the moment the program enters, multiple threads are being generated over here. Each thread is doing first a printf of hello, then it's doing a printf of world and going into next line. There is no specific order in which these threads are going. In the sense, the first thread that gets to each of these printfs, that's what will get printed. So there is no synchronization amongst these threads. Now, let's first, before we start analyzing the program in depth, let's go to a little bit of terminology of parallel computing, where we need to understand what is concurrent and what is parallel, what is synchronization. Remember that going back to the von Neumann architecture, you have this entire structure where you have an input which goes into the control unit. You have the arithmetic logic unit, the instructions and data is stored in the memory unit, and then you have an output device. Now you have a list of instructions or a sequence of instructions which basically gets executed, and that's what is a program. Now, as you keep going along the instructions, that's when the tasks get completed. Now, there could be multiple tasks which are being started at the same time. Now, you could have multiple such units over here, and these tasks will be scheduled accordingly on these CPUs. We have to see whether these tasks are being given equal opportunity to execute. Are they being organized in a synchronous manner? Do they need the synchronicity or not? So, the two most important definitions are concurrency and parallelism. So, in concurrency, what happens is that you have multiple tasks which are active, but they are not ordered, and they are sort of scheduled in some sort of a fair sense. Each of them is making forward progress, but you can see as this process 1, 2 and 0, they are all executing instructions concurrently, but they are not executing them in parallel. In parallelism, what happens is that the tasks are doing multiple things at the same time, and they are making forward progress at the same time. So, if you look at the bottom processes 3, 1 and 0, they are doing concurrent parallel execution, and this is what is happening in time. So, you can have concurrent non-parallel execution and concurrent parallel execution. So, this is something which you need to keep in mind. So, if you think of all the sum of programs which are out there, a subset of those programs would be concurrent programs, which are going in an active but unordered manner, but usually they are scheduled in some sense, hopefully fairly. In parallel programs, they are doing multiple tasks and making forward progress at the same time, but sometimes you could have parallel programs which are doing things in some sort of a lockstep. They are still parallel, but they are not concurrent, and we will look at these type of programs called SIMD programs later. So, what do we use parallelism for is to do more work in less time and also to work with much larger problems. So, essentially what parallelism does is that it exploits concurrency in a problem to run tasks with multiple processing elements. So, now let us get back to the idea of OpenMP. Let us see how we create threads, how we destroy threads, how the program flow actually proceeds. So, what happens in the program is that the initial thread will spawn a team of threads as and when needed. The moment you hit a parallel section or a parallel construct, you will spawn a set of threads, and you will keep adding these threads as and when required. So, for example, you will hit the first parallel section and you will spawn certain number of threads, you will complete that task and all the threads will then close. It will go ahead until the next parallel region is hit, and then more threads would be created and more threads would get destroyed once this particular parallel section. And you could have even nested parallel regions where one thread which has been generated in a parallel region spawns off more parallel threads, as shown in this third block over here. All these single parts are essentially sequential parts which need to be taken care of. Throughout this process, you have this sort of forking and joining model. So, let us go back to the serial code which we wrote, and let us see what is exactly happening here. So, what essentially happens here is that we have a single parallel section over here. The moment the program comes over here, it forks off and generates several parallel threads. The number of parallel threads at this moment are determined by the operating system through an environment variable. Now, each of those parallel threads will go and first say printf hello and then say printf hello world and then there is a next line character. Now, there is no synchronicity about how these hello worlds go, and that's why you have different program behavior every time it's executed. Now you can go back to the prompt and see that when I execute the program hello world, you have roughly about, not roughly, I should say exactly, 8 hellos and 8 worlds. But there's no particular order to it, right? So every time I run it, you'll get a different particular order to these hello worlds. Now, it's obvious from here that there are 8 threads which have been created. Each of those threads is doing one hello and one printf of the world. So how do we change the number of threads? This is handled through an environment variable, and that is called OMP num threads. I can now change that variable OMP num threads to something more desirable that I want. In this case, let me set it to 4. And when I execute this program, now you'll see I get 4 hellos and 4 worlds. And in this case, it's coming out in order due to a quirk in the system. But it's not necessary that we should get things out in this order. I can also change this environment variable to some absurdly large number, much greater than the number of processors that I have. For example, on this particular laptop, I actually have 8 processing cores, but I can set this to 24. That means 24 threads would be created. But since I have 8 processors on this machine, those 24 threads will get assigned one by one. So at any given point of time, a maximum of 8 would be running on these processors, and then they'll get scheduled off, and 8 new threads would come in, and they would get scheduled off, and the next 8 threads would get scheduled in. And then when we execute this, you can see at this point you get about 24 hellos and 24 worlds. And the order again is very different. Since we have no synchronization in this code. So we can also explicitly set the number of threads within the program. For example, in this code, what we are setting is the number of threads to be 4, and we are setting it explicitly inside the code. Now, then you have the parallel section. Each parallel section is now getting an ID, integer ID. It's telling me that what is my thread number, and then it is calling some program poo, which is giving its ID and some data. So essentially this function poo, which we don't know what it does at this point of time, is taking this array and taking this ID and doing some sort of processing. Can we now extend this idea to our simple hello world program? So let's go back to it. So I will now edit this program hello world, and I will now use this OMP set num threads over here, set it to 4 threads. I will also bring in this program statement. So where now I have ID, and I'm going to modify this program in this manner. Okay, now let us compile this program. Hopefully I have not made any errors. So there you go. So I will compile this program and I will put it the output to hello world, and now I will execute this program. And here it's saying hello world from some number, and it's not really giving me the exact correct number that I want. So clearly I have made some mistake in my program, which we will try to edit. So we look at this program where now we have put this integer ID and we have gotten what the identification or the thread number is over here. And then we say hello world from that particular ID. Let us compile this program and run it. Oh, I think I have accidentally closed this session, but I will restart it. Now we will compile this program. So we say fopenmp hello world.c and we'll put the output to hello world. I have made a typing mistake which I will correct. And when we execute this program, you will see that it's saying hello world from 4 different threads 0, 1, 3, 2. This is because we have explicitly set the number of threads to 4 and we are now saying hello world from each of these threads. When I execute it a second time, you will see the same output come again. But as I keep executing it multiple times, you can see that the output does not always yield the same order, because none of these threads have any sort of preference. It's essentially which thread is able to print it out first, that thread will print out its hello world, and so on and so forth. So hence, we should not get the notion that we will always get an ordered output just because these things have certain ordered IDs. Each of these threads from 0, 1, 2 and 3 are unique and do not have any preference. Okay, thank you.